There we go. So just as a very quick refresher, a total body radiation, or a TBI, it's a technique that's used as a conditioning regimen where we're preparing patients for either like stem cell transplant or bone marrow transplant. So the intent of this treatment can be either like myeloablative or immunosuppressive, and the fractionation and prescription dose will kind of reflect the intent for each particular patient. The overall goal of this technique is to deliver a homogeneous prescription dose within plus or minus 10% to the entire body. There are many different techniques that can be used to achieve TBI, and there are many of them outlined in the APM's task group report number 29. But the ones that have been pretty widely adopted generally share some of the common characteristics, where it's like 2D treatment planning, where we treat the patient at extended SSDs, typically 4 to 6 meters, and we generally utilize like high photon energies. And we utilize both of these mainly to trying to decrease the intensity fall off of the radiation beam with distance in the patient, and also attenuation losses. So there are several challenges with this technique. Mainly, even for healthy patients, this can be a pretty uncomfortable technique to undergo because it requires you to stand for long periods of time. And it's that much harder for patients who are actually undergoing treatment for these diseases. They're really frail, and it requires them to stand continuously for 20 some odd, if not longer, minutes. There's relatively large dosimetric uncertainty in these techniques, mainly because in the way of how we apply compensation to adjust for like different contours in the patient body, and also a lot of the time we correct for large discrepancies and like heterogeneity within the patient, but not for like more minor changes in heterogeneity. It requires compensator generation and block cutting for photon fields that require like lung blocks or kidney blocks. And then you have to apply the additional step of generating electron cutouts to boost up those regions that you've been shielding. So it can be quite a tedious process for preparing the treatment for delivery. And as I just mentioned, it's a relatively tedious process. And at the beginning of this, the patient has to actually stand in the position they'll be treated in, and the therapist has to actually draw the outline of the patient on the compensator tray and mark the different locations within the body, measure like the separation of the patient. And because there's so many manual steps in this process, it can be highly error prone, where it's very easy to make a mistake, and that can end up getting propagated through the entire treatment process, which would end up delivering kind of the wrong dose to the patient. Some logistical challenges with this technique is you're going to need an extra large vault, particularly for how we treat it here, because we treat at these extended SSDs, and you need all that open room where nothing's going to obstruct the open beam. For older patients, they require anesthesia. It's not really feasible to treat them with this technique because we need them to stand, but you obviously can't do that while they're under anesthesia. And if they're too tall to lie on the floor, where they're not going to be covered by the entire beam, in that situation, you have to get creative with how you actually go through and treat these patients. So in a recent survey from the Children's Oncology Group, they conducted last year on TBI techniques for physicists and physicians, 75 of the responding physicians said that they would like to introduce a more modern TBI technique, particularly those that incorporate intensity modulation, such as VMAT or tomotherapy. 100% of the responding physicians would like to reduce the lung dose for their myeloablative treatment regimens as compared to how they currently treat patients. However, only 4 of the responding institutions have currently adopted VMAT TBI, and only 3 of them have adopted tomotherapy TBI. So intensity modulated TBI is a more modern delivery and treatment planning technique that can be used to improve the plan quality in TBI. There are a couple of different options how this can be achieved, where we can use helical tomotherapy, which is done at these institutions listed here, where the benefit of tomotherapy is the couch actually moves during delivery, so it's truly helical, which makes it very easy to deliver dose to the entire body. However, while these machines can treat other forms of diseases and such, it's an entirely different machine. And if you're at a clinic that has all Linacs that work fine, it's probably not an option to replace one of them with a tomotherapy machine. So the other option for clinics that you have CR Linacs is UCSF proposed a technique where the patient would lie on the floor about 2 meters from the source, and they would do a single sagittal arc composed of many static beams where they could then apply intensity modulation to modulate the dose to the entire body of the patient. And one other technique for CRM Linacs is a multi-isocentric axial VMAT-based technique, as shown in the figures in the bottom right. And this has been adopted by multiple institutions, including us. So we have implemented this technique and treated to date 13 patients with it. And how we actually do it, I know the slide looks busy, but it basically, there's a couple of different steps we go through to treat patients with this technique. At simulation, we acquire a full body CT scan of the patient with 5mm slice thickness. And it's at the time of simulation, we need to determine if we need to treat this patient with only VMAT or both VMAT and APPA. The reason being is there's a limitation on the maximum longitudinal extent of the couch. So if the patient is too tall, where our limit is 115 centimeters, if they're taller than that, then the length of the couch isn't going to allow, or the longitudinal extent of the couch isn't going to allow us to treat them just solely as head first supine. So in this case, we simulate these patients on a special in-house developed couch, rotational couch top, as shown in the figure on the top right, which we call a spinning Manny. And this couch sits on top of the regular Linac couch, and it has a pivot bolt on it. And we're able to rotate the patient around this pivot point, so we can easily treat both the superior portion of the patient and the inferior portion of the patient. So in this case, we would treat the superior portion of the patient, everything superior to that pivot point with VMAT, and everything inferior to it with APPA. For contouring, obviously we contour the entire body, or the body structure, but then we contour the relevant structures which we're considering to spare. And the target structure for this technique is created from the body structure. And we apply here at Stanford, we apply a 3mm inner margin. Then we subtract off any organs at risk that we are particularly interested in sparing, like the combined lungs, and we add a 3mm margin on top of that, which is subtracted from the PTB body. And we also subtract kidneys and any other organs at risk that we're particularly interested in sparing. Oops, sorry. During optimization, we also typically will add flash and bolus to make the plan a little bit more robust to patient positioning. So for these patients, we'll typically have anywhere from 2 to 3 VMAT isocenters and also 2 to 3 APPA isocenters, depending on the height of the patient. For the VMAT portion, we can use either 6 MV or 10 MV, depending on the size of the patient. And then for APPA, we exclusively use 6 MV. One unique thing to Stanford of how we treat this is we mandate that the position of the isocenters, the one isocenter that's immediately superior to the pivot point, and the isocenter immediately inferior to the pivot point, are the same distance from the pivot point. The idea being that we can treat the isocenter that's superior to that pivot point, then just rotate the patient, and it will be at the correct spot So it kind of makes our lives a little bit easier and less prone to error. Ideally, we shoot for 2 centimeters overlap between adjacent VMAT isocenters, but we definitely require 1 centimeter. And for APBA, we match on the skin for the beams. During optimization, we feather the beam junctions, which is done very easily in Eclipse using the auto feathering function. One important thing is to calculate the dose from the APPA plan first, and then use that as a base dose in the VMAT optimization. Because if this is not done, the optimizer is going to have a really tough time pushing dose to the inferior portion of the patient target structure, and will result in like a really hot plan. For the APPA plan, we just do a simple field and field, and we reduce, for all the beams that are intersecting the lungs, we reduce the dose rate to keep the average dose rate to the lungs less than 20 centigrade a minute, which is done currently for historical reasons. So as you can imagine, because we're using VMAT as compared to our traditional APPA 2D technique, shown in the figure at the top right, we can simultaneously provide significantly better sparing to organs at risk, while also improving the coverage and conformity to the target structure. How we actually deliver VMAT TBI is we set up the patient and we perform a KV-KV match for the chest isocenter with a cone beam. And once we have aligned the patient at this isocenter, we enter the initial couch positions in a spreadsheet, which will then calculate the required shifts or the couch positions where the patient needs to be moved to for the other isocenters. To verify that these are correct, we add an MV port image to an arc after each isocenter shift, just to verify that we shifted to the right spot. And we didn't mix up any of the numbers. For the 13 patients that we've treated previously here at Stanford, the average treatment time ranges from 35 to around 57 minutes. And we are particularly interested in the dose being delivered to the matching or the match plane between the VMAT portion of the treatment and the APPA portion of the treatment. So we typically do nano dots on the match line just to make sure doses being delivered to that point as what was prescribed. So while intensity modulated TBI and VMAT TBI sounds great and it's can provide a lot of benefits, there are a lot of challenges with it, particularly in getting this type of program up and running. So there are equipment limitations, obviously. If you want to go the route of using tomotherapy, you have to use a dedicated machine for that, which is really not an option for a lot of clinics. As well for even VMAT-based TBI for having the special couch top. One of the main challenges in this type of technique, or VMAT TBI specifically, is it requires a special treatment geometry. It requires a lot of consideration of how you actually set up the patient and place the isocenters and beams, as suboptimal placement will result in very bad plant quality. Now, because of this and all these considerations, it can require a lot of trial and error and a lot of optimizing how you set up your plan. And because of this, the planning time for this can be substantial. For the initial cases that Natalia was doing by herself, she noted planning times that could require up to 3 days to get this up and running, or for each to achieve a clinically acceptable plan, which in general really isn't sustainable for a technique. So the goal of this work was to try and automate this planning process to really reduce the burden on the physics and dosimetry team. So we sought out to do this using the Eclipse Application Programming Interface Framework, or API framework. So rather than bore you more than I already have, I figure I would actually demonstrate how these scripts work rather than just showing you pictures. So give me a second. Okay, you guys should be seeing the Eclipse home space. So this is the research workstation. And that's where you can do all your testing of your development scripts and such. So if we go into external beam planning, the first thing you would do to actually start using these scripts is you would open the patient and you would open the structure set in Eclipse. That's all you would need. This would be after you've done all your contouring and such. One thing to note about this script that we developed is it's looking for the combination of left and right structure. So it's looking for lungs combined rather than lungs left and lungs right. And same thing with like the kidneys. So that's just one thing to note. Excuse me. Okay. So let's go ahead and launch the script. And I will give it the location of these scripts later on. And hopefully we'll move them into like the system scripts so you guys don't have to go look for them. So we go ahead and hit run. Here is the interface. So up in the top in this white region, these are kind of the global parameters that you would set when you want to auto-plan a particular patient. You can choose the structure set that you want to apply this to. By default, it pulls whatever structure sets in the current context. It sets that as the default, but you don't have to use it. You can set the dose prescription here, such as like 500 by 2 to give you a total of 10 gray. But for VMAT TBI or TBI in general, we typically use very similar regimens for all of our patients. And the most common of which are like the myeloablative, where we deliver 12 gray over 6 fractions, or non-myeloablative, where we deliver 1 fraction of 200 centigray. There's also the scleroderma trial patients, which that has some peculiarities with it, which is why we included it here. But these type of patients don't come along very often. So the most common type, or most commonly, you'll end up using these two templates. So to get started, we can, for this patient, they were actually treated with the non-myeloablative regimen. So you can go ahead and select that, and it'll automatically adjust our fractionation here. The next thing is, once we set our global parameters up here, the rest of the tasks are separated into individual tasks shown down here, from tuning structure generation, beam placement, and setting optimization constraints. So in tuning structure generation, the first thing you want to set or confirm is the inner margin that will be used to create the PTV structure. And as what kind of says in the little question mark box here, this just specifies this inner margin and centimeters that you can use. I've seen in the literature for people doing this technique, typical values range from no margin at all up to 5 millimeter inner margin. But what we use here is 3 millimeters, and that's what's populated by default. So don't adjust it unless you have a good reason for it. So now you can specify the organs you actually want to spare, or the structures you want to spare. You can do this one at a time by adding a structure, and you can select it from this drop-down list. Next, you want to select a sparing type. So for this script, I defined 2 different types of sparing. The first is we want the mean dose to the structure to be less or much less than the prescription dose. This is the case where we really want to push dose out of this structure. And we do that by not only subtracting this structure from the PTV, but also we create substructures within it, such as structures within some differential or some uniform inner margin. So for instance, we have the lung structure that we want to spare. It will create lungs minus 1 cm, lungs minus 2 cm, which we can then apply optimization constraints to really try and push dose out of this structure. When you select a sparing type, you can specify the uniform outer margin that will be applied when it's going to subtract this structure from the PTV. The other type is Dmax is approximately equal to the prescription dose. This basically says we want to be mindful of the dose that's going to be delivered to this organ, but you don't necessarily want to spare it. The idea being that you want this structure to retrieve this prescription dose, but you don't want the global Dmax or like hotspots to end up in the structure. So it just applies maximum dose constraints to this structure to try and keep those hotspots outside of it. So we can do this one by one for all the structures we want, or because we selected a template, we can just select add defaults, which will then automatically populate this list based on the structures that are typically spared for this template. If anything's missing, it'll just let you know what's missing or what it couldn't find. Now, these structures, or the way the script operates, it's not case sensitive, so you don't have to worry about typing in the structure names in a very particular way. They can be all capitalized, lowercase, mix, and lower and upper caps. Doesn't matter. The script doesn't pay attention to that. So now that we have our structures entered here, we can go ahead and hit generate tuning structures. So this little message just popped up talking about a match line, and it's asking if I want to continue. So I'm going to go ahead and hit confirm, but I'll explain what that is in a second. Mainly because I've noticed when you let pop-up windows like that hang for a long time in the ESAPI workspace, it tends to crash the entire instance of Eclipse. So this little message said, all right, it's generate all of our tuning structures and our target structures successfully. So go ahead and move on to the next part of the script. So that pop-up message that came up when talking about a match line, so the script has to look for key identifiers in your plan to know whether or not to do VMAT only or VMAT plus APPA. And the way it does that is it's looking for a structure called the match line, which is shown down here. This match line is just a single plane that's drawn at the center of the pivot bolt on the spinning Manny couch. It's an indication that you want to do, as I mentioned, VMAT with APPA, this is present. If it's present and filled, it'll go ahead and start generating the structures for VMAT and APPA. If it's present but not filled, as was in this case, it picked up on that and it's asking like, hey, did you insert this but forgot to contour it? Or did you insert this by mistake? So we created the structure set using a similar template. So it automatically inserted this, but we didn't do anything with it because we want to treat this patient with VMAT only. So we just said, yeah, we know what we're doing. Just go ahead and keep going and ignore the match line. So, and now that we generate our tuning structures, which you can see it added a bunch of different structures here, or substructures such from like the brain with a bunch of different inner margins, and same with like the lungs and also the kidneys. So the important thing is once you generate the tuning structures, you're going to want to go on to beam placement. And you don't want to close the script at this point. Otherwise, you're going to have to redo the tuning structure generation. So based off the information that you specified in this first tab, like mainly what you're going to want to spare, and also the calculated height of the patient, the script is going to calculate how many isocentrics it's going to need to cover the entire patient. And in this case, which is 3. You can specify what LINAC you want to treat the patient on. Currently, we do this on either 16, LA16, or LA17, and the beam energy, where we typically use 10x for larger patients. So I'm okay with these options for the LINAC and beam energy. And as you can see for our 3 isocenters, it also proposed names for each of them, which will then be propagated onto the names of the individual beams. It also specified or is proposing the number of beams that should be applied for each isocenter based on what you specified you wanted to spare. So these numbers are completely adjustable up to a maximum of 4. It can range from 1 to 4. So in this case, I'm comfortable with the default values that it specified. So we can go ahead and hit place beams. So what it's going to do now is actually create the plan. And the most important part of the step is determining the optimal place to position each of the isocenters, which can be one of the most tedious processes in this entire planning process. Once it's determined where to place the isocenters, it will then start placing beams and make adjustments to the orientation of that beams, which it thinks will provide the optimal coverage for this patient. So now that that's done, this little message popped up saying like, hey, I did it, it worked. You can go ahead and move on. So at this point, you can choose to close the script if you want. But what I recommend is just go onto the optimization setup tab. And based on what you specified in this first tuning structure generation tab, it's going to propose that, and combined with your prescription, it's going to propose optimization constraints for your particular case. And the intent here is these are suggestions which they don't have to be automatically applied. The idea being like it's going to propose these, but you can go through and make modifications as you see fit. Or if you need to add an additional constraint for this patient, you can do that very easily. So I'm fine with these constraints as they've been suggested. So you can go ahead and set the optimization constraint. And you know that the script is finished successfully when it gives you like this window. Basically, this is just saying that you set the optimization constraints and you've kind of finished what the script is intended to do to set up the plan for optimization. So now it wants you to close the script and like go through and like thoroughly review the generated tuning structures, where the isocenters are placed, how the beams are oriented, and like the set optimization parameters. And once you're done with that process, you can go ahead and close Eclipse and then launch the second script. So if we go ahead and close it, we can zoom in a little bit, and oops, we can see that this was our original body structure. It created our target structure, 3 millimeter inner margin, and also, for example, generated lungs with different inner margins. So now that we have this, oh, sorry, one other thing I want to note, particularly whenever it runs this script, it's going to generate 2 PTV structures. PTV body is like the main target structure. That's where all the, what you're actually going to assign is like the target structure in the plan. And there's a second one called TS PTV VMAT. That's created for particularly to where like what the optimization constraints, like that's the structure like the target optimization constraints will be assigned to. For the case for VMAT only, they will be identical, but for VMAT with APPA, they will be different. So that's just something to keep in mind. So as you can see, it created a new course called VMAT TBI and a new plan called _VMAT TBI. Please don't change the names of these until you're ready to actually prepare the plan for treatment, because the other script is looking for these particular names for both the course and the plan. And if it can't find it, it's just going to let you know, and you're going to have to go back and change it. So as you can see, we've placed our various isocenters as shown here along the patient, and we're getting fairly good coverage of it, where we have lots of overlap between adjacent isocenters. And you can see how each of the beams, it's suggested to orient them. So you can also note that from the names it proposed, which were head, pelvis, and legs, it automatically propagated that onto the beam naming to save you additional time. It automatically assigned the prescription, and it suggested the calculation model and the optimization objectives it automatically applied. One important thing to note is, well, an important limitation of our version of ESAPI is you can't set a target volume or a primary reference point. So it's going to create this plan, but it's just going to either create a reference point and automatically assign that as a primary, which you don't have control over, or it's going to grab an existing reference point. It's kind of random, like what it picks to do. So that's something you'll have to go back and change later. So that just gives kind of a flavor of how this script operates. And one other thing I wanted to show with it that you can do is, so here is a case for a patient where we actually do want to treat with VMAT only and APPA, or I mean VMAT and APPA, and we have the match plane drawn in yellow here. So this script is equipped to handle both cases easily. So we go ahead and run it. You see it, the patient's name is populated up, or the structure says populated up here. This patient was treated with a myeloablative treatment regimen, so we can go ahead and select that. And say for this patient, we also want to add flash. So we can do that very easily just by selecting this box. And we can specify the margin we want to apply for flash. Typically we use 5 millimeters, but you can change this if you want. Now there's two different options that I created for specifying flash. You can do that as either global or local. Local meaning you've created some structure that you want to create an additional outer margin and create flash over that particular region. So you can select that individual structure you want to use. Global is the other option where flash is going to be created over the entire body and then cut at the match plane. So it's only going to be applied for the VMAT or VMAT portion of the plan. So in this case, we want to add flash, it's just global and with a 5 millimeter margin. We can go ahead and add our defaults. It's missing lenses, but that's okay. And we see our structures down here. So we can go ahead and generate our tuning structures. Okay, so it generated those successfully. So go ahead and move on to the beam placement tab. And as you can see, it picked up that we wanted APPA. So our third isocyanator that we need is going to be APPA, and you can easily see that it's marked that way in the naming. So I'm fine with these numbered beams proposed, so we can go ahead and place those. Okay, so it placed them successfully, and we can move on to the optimization, where it's proposed our optimization constraints. Now note, because we added flash, it's going to assign the target optimization constraints to a newly created structure called TSPTV flash, and that's important, rather than assigning them to TSPTV VMAT. So we're going to go ahead and set that. So this is the same message it gave last time, except because we have APPA now, it's going to add another message down at the bottom. This basically says that for the APPA plan that was created, you're going to have to manually change the orientation of the patient because you can't do that in ESAPI. So we go ahead and hit OK. We can close this and open it up. And we can see that we've created our plan here for VMAT, mark underscore VMAT TBI, and then also a second plan for APPA, the legs. And you'll notice it's also in head for supine, so you'll have to change that. So as you can see, and the structure set, it created a bunch of structures with kind of this string flash in it. You can modify these structures, like how they're contoured and everything, but don't change their names because it's going to need to retain this information when you go over to the executable script. So it can pick up on the fact that you've added flash, which is important in how the plan is actually normalized, and if the script needs to run another dose calculation after removing flash at the end of the optimization. If for whatever reason you're playing around with the optimization constraints of the optimization, and you adjust them and you don't like it and you want it back to what was originally default, you don't have to do that manually. You can just relaunch the script. Okay. You can just relaunch it. You can just select your prescription. Because we added Flash, you need to indicate that, yeah, you want to use that. You can just go directly to the optimization tab and just scan the structure set. So it's just going to look through your structure set and what's in there. And from that, it's going to propose what optimization constraints you want or you should use based on your selected prescription and such. So that can save you a little bit of time if you're messing around with the plan. If you have any questions at all about how to use this script, you can either directly ask me or Natalia, or you can look in the documentation for it. So if you just really want to get up and running quickly, you can hit the quick start guide, which just kind of gives you step-by-step, walks you through how to work each process. It doesn't really give a lot of details on what's actually happening. So you can do that, access that very easily. Or if you want detailed information on what's actually going on, you can select the help button, which I put in quite a bit of effort to outline not only how to use each part, but like what's actually going on behind the scenes and why you need to do things a certain way. Okay. So that is the first half of the script, or overall script. The entire idea being like, we really want to expedite the process of preparing a plan for optimization. And from my own estimates and my experience doing like manual planning versus like automated planning as we just done, it can take a process that could take up to 2 hours of just messing around getting everything set up down to 30 seconds, which I think is pretty good. Okay, so moving on to the second script. So this script will be located on your desktops at some point. It's called VMAT TBI _op_loop MT with some version number on it. So this one, this is a simple demonstration of it. So the code in this is slightly modified from what the actual code is used. It's mainly just to kind of show what kind of output you can expect as it runs. So as you can see, the layout of the script is relatively similar to the previous script. And to start, you can go ahead and enter the patient MRN. So I'm going to enter a patient a separate patient from the ones we worked on that I already previously prepared for use with this script. So we can go ahead and open them. So as we did that, it's going to pull information from the plan, mainly the prescription here. This information here, the prescription is read-only, just as an FYI of what it should be, just as another check to make sure you have this is the right plan and everything. It's also going to pull the optimization constraints. So it'll give you one last opportunity to make any final adjustments that you want to these constraints before you start the long process of optimization. It's also going to populate a couple of the options that you can apply during the optimization. You can specify the maximum number of optimizations that should be applied during the optimization loop. You can elect to run one additional optimization after these 3 have been completed, where it'll take the current calculated dose as intermediate and really try and push hotspots down in the plan. You can elect to run a coverage check before the optimization loop. And what this is it's a simple optimization with no intermediate dose, where all the optimization constraint priorities are zeroed except for that of the target. And this basically gives an indication of, if we're just trying to cover the target, how well can we actually do it? If the plan is extremely hot, like a really high hotspot, and there's a lot of V110 in the plan, or even V120, that kind of indicates that you're missing part of the target structure, and that you should go back and kind of look at the orientation of your beams and see if you're just missing one part of the body. And lastly, there's the option of you can copy and save each optimized plan. At the end of each iteration of the optimization loop, you get a fully optimized plan. And while as the optimization loop progresses, you converge to a more like better plan quality. There may be instances where a plan from earlier or a lower iteration of the optimization loop may be more beneficial or something you can actually work on. So it may be a case where the lung dose is better for the second iteration of the plan or the optimization loop, whereas the final plan that it produces like has higher lung dose and lower hotspots overall in the plan. But you decide that you want to use that plan from the second iteration because you figure you can maintain the current lung dose while also pushing the hotspots down. So it just gives you more options to choose from if you want to do additional work on the plan after the script is finished running. Now, by default, we specify the volume receiving 100% of the PTV should be 90%. That's what's used here at Stanford. However, you can adjust this if you choose, but you should probably have a good reason if you adjust this. So now that we have all of our parameters set, we can go ahead and confirm this and begin the optimization loop. And a nice window will pop up here telling us what's going on. So, oops, we forgot to insert the couch. This will catch that and let you know, like, do you want to stop and go back and insert it? But in this case, we don't really care, so we're just going to go ahead and go march on through. In this case, it also says like, hey, you have a match line, it's filled, but you didn't put in the spinning Manny couch. Do you want to go forward or do you want to go back and put that in? So in this case, I'm just going to ignore it and keep going. So it's going to print all the parameters we set up here. And it's also going to pick up on the fact that for this plan, we included Flash. And it's going to let you know that if this is a mistake, this gives you an opportunity to stop the script and go fix it. So next, it's going to print out like what the initial optimization constraints it's going to use in this script. As you've shown here for each of the structures, the applied constraint type, dose, volume, priority, etc. And all throughout this process, it's going to continuously spit out these little updates. Like after it finishes an optimization, a dose calculation, like a normalization. And last is, once it's normalized the plan, it's going to then feed it into a function that's going to evaluate the current plan quality and decide what to do with the optimization constraints to for the next iteration of the loop. And you'll notice this takes a little bit of time because it's passing quite a bit of data around, and the size of the data is quite large. So as you can see, it finished. And now from this, it's going to tell us hold on a second. Okay, so it's going to tell us like how each of the structures that have optimization constraints did in the optimization, kind of like what the dose difference achieved was, the square of it, its current priority, and like kind of what the relative cost was in adjusting this. It'll also spit out some additional plan information for like a global Dmax, the V90 of the target structure, the V110, V120. And then it's going to tell you what it decided to do with all the optimization constraints, whether or not it wanted to adjust the dose or increase the priority. So it's going to continue going through. And it's just going to continue doing this for each of the plan. Now, one of the things with this script is you have the option to stop the calculation while it's running. And you can do this by hitting the abort button. But note that while this stopped pretty quickly, while it's actually running and doing an optimization, it will take some time for this script to actually stop. And the reason is because of the way this script was written. So the processors like actually running this script have no idea what's happening inside of Eclipse. And Peter, it's fast because I this is a modified version of the algorithm. So it's not actually doing dose calculations or anything like that. It's just telling, yeah. No, if I had figured that out, if I figured out how to make it go that fast, I'd sell that and then just retire early. But what it's doing is it's just telling, instead of actually doing the dose calculation, do a thread sleep function for 3 seconds. So as I was saying, like the processors controlling this script have no idea what's going on inside of Eclipse. So if you were to kill this script, those processes going on inside of Eclipse would still go. And it wouldn't find out that you would stop the script until it finishes there. So that can kind of create some problems in the syncing between this script and inside of Eclipse, which can lead to like open timestamps that aren't closed and things like that. So that's just something to note when you hit the support button. It may take a little bit of time for it to actually stop. So in this case, I feel like you guys kind of get the idea of what's going on. It's just going to tell you what's going on every step of the way. So if we go ahead and close this, I'll go ahead and open up that patient, and let's assume that it's gone through the optimization loop and everything looks good, which for this test case, it's not going to be the case because I just did a very simple dose calculation with open beams. So it opens up, and as you can see, the 3D dose max is really high because we didn't actually optimize this. So, but if we pretend that everything is good and we're ready to actually prepare this for treatment, the doctors reviewed it, these are the plans, and they're like, all right, this is good, prepare for treatment. What we can do, instead of manually separating out this plan into individual isocenters, which would be an extremely tedious process, what we can do is reopen that binary plugin script. And in this case, you don't have to specify anything about these global parameters. You can just directly go to plan prep. So the first thing you can do is generate the shift note. So, oops, we forgot the couch structure, and it's going to let you know that. Next, it calculated the shifts required between each adjacent isocenter and also the shifts relative to the CT reference point, which, yeah, the shifts will look something like this, which provide all the relevant information. And in addition, saying like, after you shifted to the isocenter, the pelvis isocenter, go ahead and rotate the spinning Manny and then deliver the APPA. Now, the next part is separate the plans. So one thing is that in our current version of ESAPI, we can't add setup fields, but we can copy plans. And if they contain setup fields, we can kind of propagate that through. So if we just make multiple copies of a plan, it's kind of a way around adding setup fields. So if you had added setup fields, this would just kind of propagate that through the process. But in this case, we didn't add any, and I'm okay with that. This also picks up on if you've added Flash, and it will go through and ask you if you want to remove them, which I said yes to. So it's going to go through and get rid of all the structures that were associated with Flash, and then separate the plans out into their individual isocenters. One consequence of getting rid of the Flash structures is because it has to operate on this structure set, as you can see here, it has to wipe the calculated dose and all the plans that reference this structure set. So you can, this button will appear, which gives you the option to go back and recalculate it through the script. For plans that did not have Flash, the dose will be retained through all the plans. You don't have to recalculate dose. So, and there's going to be more features coming in version 16, such as adding setup fields, setting like the primary reference point, adding plan sums, all of that. So, and as you can see, it created or separated all of our plans. And to just our individual isocenters is shown here, which will hopefully save quite a bit of time. Okay, so that was just kind of like give you guys a little bit of a flavor of how these scripts operate. I highly recommend you, see if here we go. I highly recommend you go into the Eclipse research station and just play around with it. Let me know if you find any bugs. So this is cool and all, but like, what did we actually achieve with this? Like, does it actually work? And yeah, so we compared 10 patients that we had previously treated with VMAT TBI. The manual plans that were actually manually done by a physicist or a dosimetrist, we replanned them using these scripts. And you can see a screenshot of the coronal dose distribution for the manual plan on the left and the automated plan on the right. And you can see they look very similar. Quantitatively, we analyzed 6 metrics of interest to us for this particular technique, particularly the global Dmax, the volume receiving 110% of the prescription dose, the D-main to the lungs and lungs minus 1 cm, and also the kidneys D-main, and then the bowel Dmax. We computed this for both the manual and auto plans, and we computed their mean difference and the standard deviation. We also performed a one-sided t-test to evaluate any significant differences where we assumed anything less than 0.05 was statistically significant. For everything we evaluated, there were nothing was statistically significantly different except for the lungs, where we achieved superior lung sparing with our automated plans. Now, we also want to get physicians' opinion of this. So we currently prepared these plans. We basically blinded them, so you can't tell which plan is which. And we gave them to 3 physicians and asked them to evaluate. And only one of the physicians has given us feedback yet. The other 2 are still working on it. So those results are coming soon. So in conclusion, we developed an automated planning process for VMAT TBI in the ESAPI workspace. We attempted to develop the scripts to be modular, user-friendly, and very flexible, not something that's going to coerce you into doing something a particular way. We achieved statistically significant lung sparing with the same target coverage and similar Dmax to the manual plans. And we observed substantial reduction in the planning time, where the initial estimates of 2 to 3 days were reduced to 3 to 5 hours. Like now we can get a sim of a patient late morning, perform the contouring early afternoon, run the script, and then have to give it to the physician. They approve it that night. So it makes this technique far more feasible. Because we've gotten such positive initial results of these scripts, we've already thrown them into clinical use. Future work includes providing additional refinements to the auto planning algorithm to improve our achieved plan quality. And with that, thanks very much, and I'll take any questions.